So this is a quick presentation on Hyperledger Sawtooth, which is a enterprise blockchain platform, open source. It's part of the Linux Foundation's Hyperledger project. And these slides are by Sawtooth maintainer, Dan Middleton, so credit to him for that. I'm also a Hyperledger Sawtooth maintainer. And yeah, so what we're going to talk about today is some of the design motivations behind Sawtooth, why we built it the way we did, why we think it addresses some of the interesting problems in blockchain space. We're going to talk a little bit about Sawtooth 1.0 that released pretty recently, so some of the key features there. And we'll also go over how you'd actually develop an app on Hyperledger Sawtooth. So there's a quick overview of everything, but hopefully we touch on something interesting for everybody. So first, announcing Hyperledger Sawtooth. This is from the press release. It was January, February that we finally pushed 1.0 out the door. This is a big step for us, means that our APIs are stable. We're committed to supporting them going forward, at least until we hit 2.0, which is not going to be for maybe ever, but we'll see. And just a special shout out to all of our open source partners. A lot of people helped make that happen. And so they're all there. Cool. So really quickly, before we dive into Sawtooth, let's make sure we're all sort of on the same page about what a blockchain is or what a distributed ledger is. I might use the two terms interchangeably. I think they more or less mean the same thing. But the basic idea is you have a peer-to-peer network. You have a bunch of nodes. And those nodes all have their own instance of a database. That database or ledger is completely identical on every single participant in that peer-to-peer network. And part of what helps make that happen is that the data is organized into discrete blocks of updates. And those blocks are then linked to the previous block, typically by a hash. So if you modify a previous block, it's going to invalidate any blocks that came after it, which means all of these discrete sets of transactions are inherently linked together. You can't go back in time and modify something without ruining the whole database. So why might you use a blockchain? The key strength of a blockchain is that it can algorithmically enforce trust. So you have a bunch of organizations or a bunch of entities. Bitcoin is the original blockchain. It's the classic example. A bunch of people who would love to spend each other's money if they could get away with it. But the blockchain enforces that trust, and there's no trusted third party. There's no bank in between the people who are making those transactions. It also offers an immutable transaction history because everything's organized into blocks. You can't go and change them later. And it also offers high availability because it's a peer-to-peer network. So long as not too many nodes go down, you're going to be able to access the blockchain data. Consensus algorithms that offer things like crash fault tolerance and Byzantine fault tolerance can help ensure that the data is accurate. Now, why not blockchain? So I work with Sawtooth. I work with a lot of companies developing apps for Sawtooth. And oftentimes the conversation I have with them is why they shouldn't be using Hyperledger Sawtooth or any blockchain. I think it's the hip new thing, so everyone wants to use it. But first of all, if it's an internal process that you're running, if there's no other business partners or anyone else, all the data is being kept and controlled internally, like, there's a great thing for that. It's called a database. Like, just use that. It's really mature, really well developed. So any centralized architecture is going to really destroy the main utility of blockchain, which that it is distributed. And there's also some weaknesses to blockchains, which even if you want that distributed nature, might not make it the best solution, at least now. Throughput is one of them. Any financial network like Visa or MasterCard or like stock trades, those are happening in the order of like millions of transactions per second, whereas a blockchain is going to be more like at best thousands of transactions per second, and probably not even that much. because you're not sharing the load. Every single node is doing all of the work. So it's a tough thing to scale up. It is an active area of research. And then the other thing is, if you need your data to be private, you know, one of the key areas of key aspects of a blockchain is that the data is very transparent. So that's a tough hurdle to overcome. We'll see what clever stuff people come up with going forward. There aren't really great solutions for either of those right now. Cool. Moving on. So with Sawtooth, we approached the strengths of a blockchain and tried to really play to those. We designed it to scale. It features a novel consensus algorithm called POET, which we won't talk too much about, but that is a very scalable consensus algorithm, unlike proof of work. And it also features swappable consensus. So if something better comes along that is more scalable, we can always switch to that. We really focused on ease of use for people who are developing and deploying. You can write applications on Hyperledger Sawtooth in a variety of languages, Python, Go, Rust, JavaScript, and you can deploy it pretty easily. I was going to make some point about that, but I forgot it, so it's going to be a secret just to me and me. Also, we're very focused on keeping it distributed. Some other enterprise blockchain platforms out there kind of like skirt the definition of what a blockchain is a little bit and tend to be a little more centralized, a little less distributed. So Sawtooth is really focused on maintaining that distributed nature of blockchains. Yeah, we also provide a really well sequestered sandbox for smart contracts to run in and help keep that safe. So I'm going to talk a little bit about 1.0 architectures and features, some key things we want to highlight. So a couple of big features. We have parallel execution of transactions. We're pretty proud of this. It took some doing to get it working, but each node in that peer-to-peer network, each validator, is smart enough to take a look at a batch of transactions that it's got to validate and figure out which ones it can execute in parallel and which ones need to be executed serially, and validate the ones that it can in parallel, which can speed things up a good deal. We've also got a lot of SDKs out there. I'll talk a little bit more about the languages that are available later, but we're also continuing to build that out. And if you want to go full manual, technically any language that supports the networking protocol 0MQ, you could write for Sawtooth in. So that's cool. On-chain governance. So this is the deployment feature I wanted to talk about earlier. All of the settings for Sawtooth, for a Sawtooth blockchain, live on the blockchain itself. And the big advantage of this is if you're deploying a bunch of nodes to a bunch of different computers, then you don't have to make sure you copy over the config files. If a new node joins your network, as soon as it pulls down the blockchain, it can see what the settings are. The settings are also tied to a block. So with any given transaction, right, it needs to be validated in a deterministic way. So it's possible a setting might change whether or not a transaction is valid. But so if you have a transaction in block A, say, and you change a setting in block B, when a later node plays back through the block to validate everything, it's going to know what the setting was in block A because it hasn't been changed yet, and then change it in block B, and then from then on, the settings in block B would apply. So it's pretty nifty. You can change all sorts of things up to and including the consensus algorithm. So POET is one of the options available. There's also a POET simulator. There's a dev mode consensus. We're looking at adding a couple of others like Raft, PBFT. So if you wanted to switch to one of those down the road, or if POET got upgraded or something like that, you wouldn't have to redeploy your network. You just change the setting and off you go. And then there's also a few distributed applications we have as part of the core code. One of them is Seth. which is pretty excellent, actually. It's a runtime environment for Solidity code. So you can actually run your Ethereum smart contracts on Sawtooth by using the Seth transaction processor. And supply chain is a platform for supply chains. It tracks the provenance of goods, as well as some like things like telemetry information, temperature, stuff like that. So let's talk about the actual architecture. This is sort of the most basic bird's eye view of what you're going to be looking at. In the middle there, you've got a validator, which is what you're going to be pulling down from the core Sawtooth code or from Docker Hub or whatever. And that is sort of the middleman that validates transactions and blockchains and all of that stuff. Over on the left, there's going to be a client that you probably wrote yourself. And that is the thing that will be submitting transactions, right, to the validator, as well as querying what the current state on the blockchain is. And so the validator then mediates that access to the database, decides who gets to access what, as well as validating the transaction boilerplate. And then finally, the transaction processors, it's going to be another piece that you would probably write yourself, although if you're running Seth, say, that's a pre-built transaction processor that can run your Ethereum code, so you wouldn't have to modify that. But oftentimes you'll write your own transaction processor, and that's what handles the actual business logic of the payloads. So each transaction has a payload. That payload to the validator is just a set of bytes. It has no idea what it is. It just validates all of the cryptographic stuff around the payload, and then sends it off to the transaction processor, which will then decide what to do with the payload itself. Looking at it in a little more detail, you can obviously have multiple clients connected to your validator, multiple transaction processors. You're not limited to just one. You can deploy as many as you need. In fact, every validator deployment is going to have at least one transaction processor, which is that settings transaction processor that handles changes to settings on chain. And you'll also be connected to one or more other validators in your peer-to-peer network. The only new piece in here is the REST API. That's a separate process that takes that 0MQ networking, which is going through that interconnect there, and translates it into HTTP JSON. So you don't necessarily have to use the REST API. It's an optional process, an optional component. But typically, it's easier to write against HTTP. It's what people are used to rather than 0MQ. So you can do that with your clients. And then, yeah, taking a look at a couple of these pieces. The transaction handling, that's where it's going to figure out that parallel scheduling. It's going to look at the addresses in state that a particular transaction wants to read from, wants to modify, and organize the schedule for handling transactions such that it can parallelize the ones it can and serialize the ones it can't. That means you can have multiple transactions per block affect the same address in state, which is not something that every blockchain out there can do, actually. Some of them need to would need to split that up over multiple blocks. So that is handy. Okay, multi-language support. So right now we have SDKs written for Python, JavaScript, Go, and Rust for writing that client code for submitting transactions, basically, and to a lesser extent, reading state, which is basically just an HTTP request. So there's not that much in there for reading state, but yeah. So those are there, and the Rust one I think is actually done at this point. Has all the features in it. And there's a few more on the back end. In addition to Python, JavaScript, Go, Rust, you've got C++ and Java that you can write transaction processors in. So it's a pretty wide range of languages you can work in as of today. And we can always add more SDKs. Like I said, any language that supports 0MQ. A member of the community, someone who's not a Sawtooth maintainer yet, wrote a .NET SDK, which is pretty cool. So that's sort of working its way through. I'm not sure what state it's in, if it's feature complete yet, but that's something they're working on. might be a couple of others in the works as well. There's a closure one kicking around somewhere. All right, Seth. What does Seth do? So Seth has a few parts to it. We've got the Seth transaction processor itself. That's the thing that interprets the Ethereum smart contracts. And then that runs alongside a few other built-in transaction processors that come out of Sawtooth, the block info, settings, and identity transaction processor. I won't go into too much details about those, but those provide information that Seth needs in order to interpret Ethereum transactions. And those are things that come out of Sawtooth core that you might run for your own purposes with your own transaction processor. They're not necessarily Seth specific. And in addition to the REST API, there's also another front end, a JSON RPC interface. So that can interact with some Ethereum tooling out there like Remix and Truffle. Though it's work in progress. I'm not sure what state that's in yet. On-chain governance. So these are our settings. And it's pretty straightforward. So you set a key, and we namespace those keys. So for example, that top one there, sawtooth.poet.targetWaitTime. Poet is the consensus algorithm, and an important setting for that consensus algorithm is it needs a target wait time. So in this case, we've set it to 5. We could change that later if it wasn't working for us. And you would change it by submitting a proposal to change it. That's just a transaction. And then it goes through a voting process, and that's another setting, how you want to go about voting. So you can set it to simple majority, 2/3, 100% consensus before a setting goes in. And then people would respond to that proposal, voting up or down. If and when it crosses the necessary threshold, the setting goes into effect. And yeah, you can see a couple of other common examples there, like how many transactions to allow per block and what transaction families to allow. You don't necessarily need to limit the number of transaction families. It can just be all of them. But for a production deployment, you'd probably want to set explicitly what you're planning on running. So one of the features that setting allows us to do is dynamic consensus, and pretty straightforward. Set consensus to Poet, the voting happens, it goes through, now you're running Poet. A quick word on the difference between Poet and Poet SGX. So Poet SGX is assisted by hardware, specifically the SGX chip that's on most recent Intel processors. That provides you a trusted execution environment. In theory, someone else could come out with a chip with their own trusted execution environment. That hasn't happened yet. So Poet SGX is limited to Intel hardware. The advantage of it is that for essentially negligible processing power, you get the same Byzantine fault tolerance that proof of work allows you. So that's pretty nice if you can deploy on all Intel chips, or down the road, if other chips come out, you can make sure you're deploying on a trusted execution environment of some sort. In the meantime, if you can't do that or what have you, there is a Poet simulator that doesn't give you the hardware assistance, so you can't ensure Byzantine fault tolerance. You can ensure crash fault tolerance, which basically just means the data, you can ensure that the data is all the same, is correct, but you can't ensure a bad actor doesn't deliberately fool you. Yeah, so we'll talk about actual app development. I think, so one quick point I didn't touch on earlier, I should probably add a slide for actually. If you are only familiar with Bitcoin, Ethereum, you might only be familiar with the concept of a public blockchain and not heard of a permission blockchain. So with Sawtooth, you could, in theory, build a public blockchain, but it's really engineered for a permission blockchain, which means you've got multiple parties. They don't trust each other, but it is a limited set of multiple parties. A few banks or a few dozen banks that want to agree on some data but don't trust each other, right? Which is, so that's sort of a key feature of a lot of enterprise solutions out there right now. Sawtooth is flexible enough that you could go the public route as well, but that's not the focus. All right, so let's actually develop some apps. So you're going to be responsible for two major pieces when you develop an app. And we sort of group these under a transaction family. It's a general term and basically means just all the business logic that has to do with your type of transactions. So typically a transaction family includes your clients, where the transactions are created, your data model for state, what addresses are you going to use, and what do the actual entities being stored in state look like, and the actual business logic of going through the payloads and deciding what gets saved to state. All of these pieces are entirely up to you in how you want to design your transaction family. The validator doesn't care what data you store to state. To the validator, it's just bytes. Same with the payloads, they're just bytes. It passes them along, and it handles all the stuff around that data, the consensus, the blocks, et cetera, et cetera. So you can think of a transaction processor sort of like a smart contract. It is what's going to encapsulate the business logic of your transaction family. And I already talked about this a little bit, but it can be as complicated as a virtual machine or as simple as just like set this key to this value. And one of the cool things about this is these concepts can coexist on the same blockchain. So you could have a transaction processor or a set of transaction processors, some of which handle very simple transactions that can afford to be simple. For example, a Bitcoin transaction is very simple. It's just like, change this quantity at this address. And so you could just have a transaction processor that's hard-coded to do that. But then maybe you want to have, there's a couple of more unusual transactions that are going to be based on smart contract logic, bytecode that's actually stored on the chain. And you could have both. The choice is entirely up to you. So what's the workflow between the transaction processor and the validator look like? First, the transaction processor is going to start up. It's going to register with the validator. Then at some point that a transaction is going to come in, right? And the validator is going to call an apply method that's been defined on the transaction processor. And that apply method will get past the transaction. For a transaction to have gotten this far, it means that the signature's already been validated, all the sort of cryptographic stuff, all the boilerplate has been handled and validated already. And now it's basically just up to you to decide what to do with the payload and whether or not that payload is valid according to your business logic. Assuming it is valid, you're then going to send some get and set requests back to the validator to either get or set data in state. Okay. So the client then is pretty flexible. It can be whatever you want. It can be like a browser app, a mobile app, a command line interface. It can talk to the built-in REST API, or something we've done a lot, like with Sawtooth Supply Chain, for example, is the client is actually like a whole client architecture with a custom REST API that is talking directly to the validator through 0MQ, as well as some other pieces like a process that syncs state database or syncs state data to a local database. So you can have sort of more robust queries of the blockchain data, doing something like that. And then there's also a number of web apps that talk to that REST API. So they can be sort of as simple or as complicated as they need to. The basic job is going to be to create those transactions and batches. We'll talk about what batches are in a second, and then submit them. So the data structure that the client is really going to be worried about or the two data structures are transactions and batches. So Sawtooth has this concept of batches, which is pretty unique in the blockchain world. And basically a batch is a collection of transactions that you submit together, and the batch itself is atomic. So typically the transaction is what's atomic in a blockchain. Either the whole transaction gets applied or none of the transaction gets applied. With batches, you can link multiple transactions together and say, I either want to apply all of these transactions, or if one of them fails, I don't want to apply any of them. So you can have a batch that's just one transaction. You don't need to batch multiple transactions together, but if that's a functionality you need, that's there. And so the batch itself is pretty straightforward. It has a header, which is encoded as bytes. The header is what actually gets signed cryptographically. So the signature is included there as a string. The header signature also serves as a unique ID for the batch. So if you need to reference it later, you'd use its signature. The batch header, if you were to deserialize it, you would see the public key of the person who signed it, and you would see the IDs of every transaction you have included in the batch. So that's how it all gets sort of linked up into the signature. So if any of those IDs in the transactions were to change, it would no longer match what's in the batch header. The transaction itself looks a lot like a batch. It's got a header, which is bytes. It's got a signature of that header, and it's got a payload rather than transactions. That payload is also bytes, totally opaque to the validator. The validator never really touches it except to validate the header. So the transaction header is a little more complicated than the batch header. It's got a number of keys. I'm not going to go into too much detail about them all, but you'll notice there is a hash of the payload. So that's the only sort of validation of the payload the validator is going to do, is they're going to check and make sure the hash matches the payload bytes it has, so the payload hasn't been tampered with. There are the public keys for both the signer of the transaction and the signer of the batch. So it can make sure that a transaction hasn't been snuck into a different batch than you thought it was going to be a part of. The family name and the family version, that's basically routing information. That's how the validator knows where to send, which transaction processor to send the transaction to. So you'll have your family name, whatever it is, and then you can also have multiple transaction processors with different versions running potentially at the same time. So you can version your transaction processors as well. Inputs and outputs are the addresses you're going to be writing to state. You can wildcard these and you can prefix them, but ideally what you want to do is have your client understand the same logic that the transaction processor does about how to calculate the addresses it's going to use. Because if you can specify the exact addresses you plan to read from and write to in state, then the validator can do a better job of parallelizing the transaction execution. And then dependencies are other transactions that you have to wait on. Those would be other transactions not in the batch. Cool. The data model that lives in state, that's totally up to you. It can be anything you want. We use protobufs a lot in our Sawtooth development. It's a pretty good data encoding format, but the important thing is that both your transaction processor and your client understand what the data model is, because your client is going to be encoding that data. If in a payload, the transaction processor needs to decode that payload, and then it's going to encode some data in state, and the client needs to know how to decode that state data. So yeah, make sure you agree on that. And then the addressing scheme, in state, there is a Merkle tree, which you don't need to know what that is. Just know that you have a 70 character address to play with, 70 hex characters. The first 6 characters are the namespace for your transaction family. The next 64 characters are yours to play with however you want. So you can set thing, you oftentimes what we'll do is we'll do like a hash of the unique ID or something and save state there. You can, with the Merkle tree, you can fetch anything under a prefix. So like you could say anything that matches the 6-character namespace, or anything that matches the first 12 characters. So oftentimes you'll sort of sub namespace that address. But yeah, that's the general idea. If you want to see some of this stuff in action, there's a lot of code out there, and you can go ahead and check it out on these links. And yeah, as well as the documentation, the dev guide at the bottom. But there's been a lot of apps developed on Sawtooth already, and they're continuing to mature, take shape. So go out and give it a try. Check out some of the tutorials. Maybe explore your own use cases. Help us with code, docs, examples. It's actually, now that we've gone through 1.0, the community is really starting to grow, starting to pick up, but we're always looking for more people playing around with it, contributing. Some more links in the bottom there. And yeah, that's it. Thanks.